Good evening, everyone. Uh, Welcome to the Radio Astronomy Techniques seminars. This is the second edition of this series. It is my pleasure today to welcome Dr. Amy Kimball to give a talk on the VLA Sky Survey. I'll introduce her to you briefly. So Dr. Kimball, she completed her PhD from the University of Washington in 2010, after which she was a postdoc at NRAO, the North American ALMA Science Center at NRAO in Charlottesville, where she supported users of the ALMA telescope and also continued to do her own scientific research. After which she held a postdoctoral position at Sydney, Australia at the CSIRO Astronomy and Space Science Division, which runs the Australia Telescope National Facility. Besides her research on quasars, she was a support astronomer for the ATCA and was a member of the commissioning and early science team for the Australia Square Kilometre Array Pathfinder ASCAP. Currently, she holds staff scientist position at the National Radio Astronomy Observatory, where she works to support users of the Very Large Array Telescope. And she holds the position of the head of operations of the VLA Sky Survey. And she is a group lead for the pipeline operations support and oversees the quality assurance of the science-ready data products from the VLA. So welcome, Amy. We would be very happy to hear about the VLA Sky Survey. Over to you.
Okay, thank you. Yes, let me turn back on the screen share. Okay, can you see my main? Yep, okay. So yes, I'll be giving an overview of the VLA Sky Survey. There's a lot that I could talk about for a lot longer than this talk, but I'll try to do my best to give the overview in a timely fashion, and I'm happy to take questions during as well as after. So I'll start by just reminding everyone that we're using the Carl G. Jansky Very Large Array, or VLA, which is in a Y shape. There are 9 antennas along each of three arms, and here it's shown in its most beautiful configuration, where it's everything's very compact. It actually has oops, here we go. It's located in New Mexico, which is shown in the orange there, between Arizona and Texas, and then the star shows the location of the VLA. And can you see my pointer, by the way, if I want to use it?
Yes.
Okay, great. And so here it is on the planes, and we move it through different configurations. A is the most extended, D is the most compact. For the VLA Sky Survey, we use the B configuration, and that's to get a resolution of approximately 2 arcseconds. It's more like 2.5 arcseconds because it's a snapshot survey, whereas the resolutions over on the left are showing basically the resolution you would get with a full synthesis observation. So first, why are we doing a sky survey, and why now? So I think everyone is aware that sky surveys are really where a lot of data is coming from. Recently, over the past few decades, the VLA had legacy surveys, NVSS and FIRST. You don't need to be familiar with them, but just to know that they were both done in L band, so basically at 20 centimeters. And it's been 25 years since those surveys. We're several years before SKA1 and the next generation VLA, which will be under construction later this decade. And right on the horizon is the Rubin telescope's legacy survey of space and time in the optical. So it's quite timely to be doing a survey now. And this is a quite high resolution survey, which is crucial because multi-wavelength and multi-messenger surveys in optical and all other frequencies and gravitational waves as well, need very high resolution in order to match their own resolution. And with the time now in between the legacy surveys and SK and GVLA, we can start building up a time series for time domain studies, which is one of the main scientific legacies of the VLA Sky Survey will be transients and time domain studies. So this was a survey that was driven by the community. It was proposed to use certain new capabilities of the upgraded Karl G. Jansky VLA. And this was proposed to the NRAO director and reviewed by an independent panel and approved by the NRAO director in 2015. So what were the scientific capabilities of the upgraded VLA that are important? So on the right, I'm showing a little cartoon. The orange shows the regions of the electromagnetic spectrum from 1 to 50 gigahertz from L-band to Q-band that were accessible to the pre-upgrade VLA. The post-upgrade VLA, the Karl G. Jansky VLA or the Jansky VLA, all of 1 to 50 gigahertz is accessible, including the S band from 2 to 4 gigahertz, which was not part of the observing for the pre-legacy VLA. And the Karl G. Jansky VLA has up to 8 gigahertz of instantaneous bandwidth accessible. So this allows much better continuum sensitivity, spectral index information within a single band, allowing rotation measure studies with polarization, and very high survey speeds for wide field surveys. The correlator is extremely flexible. And what's particularly important to allow us to do the VLA Sky Survey is this new observing mode called on-the-fly mosaicing, which I'll talk about more in a second. And this decreases the time overhead for very large, relatively shallow surveys. But even relatively shallow is quite deep compared to what could be done with the pre-upgraded VLA. So here's the definition of the VLA Sky Survey. There were actually several different types of surveys that were proposed that were reviewed, and this is the one that was chosen. So we're observing in S band, which is 2 to 4 gigahertz. The angular resolution is approximately 2.5 arc seconds. That's using the B configuration as well as a hybrid configuration of the VLA. We're observing with 2 megahertz channels and in full polarization. And the survey is synoptic. So we're actually observing the sky 3 times, separated each epoch by approximately 32 months. So it's very good at picking up slow transients or things that have suddenly appeared or have disappeared. So the amount of observing time, we're observing over 6 different configuration cycles of the VLA. So we do half of the sky, the first cycle, then the second half, the second cycle, then we went back to the first half, then back to the second half, and so forth. And it's about 5,500 hours total that we'll be observing. And so we just have some statistics in this little table. So we're observing everything that the VLA can see. That's the sky north of minus 40 degrees declination. In one epoch, we reach a 1 sigma RMS of approximately 120 microjanskis. So with the cumulative images, combining all 3 epochs, we'll reach approximately 69 microjanskis per beam sensitivity. And we expect 5 million detections of sources in the cumulative survey. So the survey's lifetime is 7 years, and we're actually quickly approaching the end of that. We're actually observing the last half of the 3rd epoch right now, and we expect to finish in October. So just a brief overview of the main science themes. Oh, I just realized I'm not in presenter view. I'm going to stop my share for 1 second, if that's all right. Apologies. Okay. No, can't quite see that. Okay, I will have to just remember instead of using my notes. So the galaxy evolution through space and time indicates that we're observing radio sources over the full evolution of the universe. What's shown in this graphic in the top left is the same radio source as it looked in the 2 legacy VLA surveys, NVSS and FIRST. And those were both done at 20 centimeters, as I said, but they were done in different configurations of the VLA. So NVSS was purposefully low resolution. First was higher resolution, and VLASS is that even higher resolution. This is a really nice source that we can see separates into two sources with jets, which is just very cool. On the top right, we're showing a polarization image that was made, or not a polarization image. The grayscale is the image, and the pink show the direction of the magnetic field lines. And this is from a pilot observations that were done in preparation for the VLA sky survey. So we're going to get nice high resolution polarization data for many double lobe sources and other extended sources, radio galaxies, and so forth. In the bottom left, this is just indicating that we're observing the transient universe. So we're getting lots of quasar jets that have turned on suddenly, or supernova remnants, all sorts of interesting transients. And of course, because we're observing in the radio, we're able to peer through the dust in the Milky Way galaxy and study all sorts of galactic objects as well. So before I continue to talk about this, I want to point out that the VLA Sky Survey is a really large endeavor that NRAO is doing as a service to the astronomy community. And many people are involved, and I can't possibly list all their names. I can barely list all of the groups at NRAO that have been involved. So just reminding you that I'm the head of operations for the VLA Sky Survey. The management team consists of the project director, project scientist, and the technical development lead. And I've put in orange the VLA data analysts. So this is the team who really is the boots on the ground, working with doing all the nitty-gritty stuff, the quality assurance, looking at all the data that comes off the VLA, including not just the VLA Sky Survey, but if you have VLA observations, the data analysts are looking at your data as well. So it's a really great team that we have, and it's an effort that takes a lot of hands, a lot of cooks. Okay, so I want to start by talking about some of the observing challenges for the VLA. So here's a description of on-the-fly observing. So instead of the standard way of observing in the radio is you slew to a source that you're interested in, and then you sit on it and you integrate for a while until you build up as much sensitivity as you want, and then you slew to the next source, and so on. One issue with this is that the antennas, which each weigh well over 200 tons, every time they move, they have to take a little bit of time to get up to speed, and then they take a little bit of time to settle down after they've moved to their location. So for a relatively shallow survey, the VLA Sky Survey effective time on source for a single epoch is just 5 seconds, and it's still quite deep, again, getting to 120 microjanskis, 1 sigma sensitivity, but it's only 5 seconds effective time on source. And so the overhead time of an antenna that it takes to slew and settle is more than that. It's about 7 seconds. So the overhead time that would go into a survey that you did with your sort of regular, point and shoot would make it basically infeasible to do in a reasonable amount of time. On the fly observing is the antennas are constantly in motion, slewing back and forth and taking data as they move. And so we're taking very fast integrations so that we don't smear out the data. So the integration time is 0.45 seconds. That's every integration. And that allows us to build up 10 integrations across the primary beam. So the separation between any two integrations next to each other is 1.4 arc minutes. And every time, so we scan in one row approximately 10 degrees in right ascension, and then we shift by 7.2 arc minutes and and then slew back in the other direction, constantly taking data. The row separation of 7.2 arc minutes was chosen to reach a certain level of noise homogeneity. And I have a link to the observing document that shows the formula to basically determine for any mosaic, whether it's your standard point and shoot or OTF, sort of what separations you want to use between rows and between individual integrations. So we've divided the sky up into tiles, each of which is approximately 40 square degrees. So here in this graphic, I'm showing two tiles on the sky next to each other. They're typically 4 degrees tall and 10 degrees wide in right ascension. And it takes about 2 hours to scan over a single tile. That includes observing the observing overheads for a complex gain calibration. We slew to a phase calibrator or a complex gain calibrator every about 15 to 20 minutes. So showing here, it's not it's not exact. It's just a graphic. But the way it works is that we slew to the end of one tile and we stopped the integrations, and then we slew back in the other direction. And then when we have the neighboring tile, we do the same thing. And the separation between the integrations is such that if we were doing a constant slew across 20 degrees, then we would have the same separation as we end up with. So 2 hours is about the most we can do, because the tiles are rising and that we have certain elevation limits, and so that was a fun puzzle to figure out the tiles on the sky. So this is just a video that I think is kind of fun that shows the VLA observing a VLA sky survey observation. So you can see the antenna slewing back and forth, and then after a few rows, it goes to a complex gain calibrator, and you can see it's rising in the sky as the tile is rising, and at some point it finishes this tile, and then it goes back down toward the horizon and starts on the next tile. So this is, of course, highly sped up. This is about 4 hours of observing, and I just think that's a fun video. How do I move now to the next slide? There we go. Okay, so as I mentioned, we're observing as far south as -40 degrees. And so how do we achieve reasonable resolution even when we're observing very, very close to the horizon? So what we do is we actually, so first imagine, so we're in this B configuration, observing most of the northern sky. And so from the point of view of a source in the sky, what you see is this upside down Y shape, which is roughly equilateral. But imagine if you're a source very far in the south and you're viewing the same configuration of the VLA, it's foreshortened, and so you see a foreshortened northern arm, and so you would end up with a synthesized beam that was very wide in one direction and very narrow in the other direction, and basically wouldn't have very good resolution. So we actually use a hybrid configuration known as the B North A, where the east and west arms, those are the two southern arms, are in the B configuration, the standard B configuration, and the north arm is extended into the A configuration. So the projection of this to the southern sky looks more like the standard B configuration, and we achieve roughly the same resolution of about 2.5 arc seconds. So we observe the sky south of -14 degrees declination in this hybrid configuration. So one of the big challenges, of course, is RFI. So on the bottom here, there's an ARTIS impression based on real data showing where satellites are surrounding the Earth, and you see we're just completely surrounded. Also near the VLA, there are towers for satellite downlinks for satellite communication, and those are in the lower and the upper bands, as well as in the lower part of the band around 2.2 to 2.4 gigahertz is where the Sirius XM satellites communicate. So on the top left, I'm showing the results of an RFI sweep, basically over a range of hour angles and across the S-band. So where it's black is good, and where it's white is bad. That is where it is saturated. So that's a problem for us. So we first try to avoid that by not observing parts of the sky where we know the satellites are. So what happens when if we slew over a satellite, we actually move into gain compression. So basically the antennas are basically, they're electronic. They basically convert an electromagnetic signal from the sky into voltages. And so a certain signal in leads to a certain signal out. And what you want is a linear gain. So if you have twice as much signal in, you get twice as much signal out. But at some point this saturates. So if you receive too much signal in, you can receive more and more signal in, and the out signal is the same. And so you can't revert from what you're voltages that you have out to what the electromagnetic signal was in, and that's known as gain compression. So on the top left, I'm showing the gain compression measured over time. And basically, every time that sinks down, that's where we're slewing over a satellite. So on the bottom here, we're showing basically an RFI sweep that shows the amount of gain compression as a function of hour angle and declination. The Sirius XM satellites sit at about -5 degrees. That is the location of the Clark belt from the point of view of the VLA. And you can see so the red is where the compression is worse than 20%. And it's actually, it actually covers a much larger region than just where those satellites are. And we think the reason for that is that the S-band receivers, while the antennas might not be pointing directly at the satellite, if you're pointing near in the sky to the satellites, then the S-band receivers may actually be able to see the satellites, to see around the secondary reflector and see the satellites. So we first try to just avoid observing in those regions of the sky where the compression is worst. I now want to talk about the basic data products. So this is what NRAO is producing for the community. So first, I'll point out the amount of data overall is about a petabyte. So the amount of raw data over the entire survey is going to be about half a petabyte, and the data from the images, it's going to be about another half petabyte. So as soon as data are observed off the VLA, so that's VLASS as well as other data, it goes into the archive immediately. Normally, there's a proprietary period of a year where that data is locked for anyone but the PI and the COIs. The VLASS has no proprietary period, so the raw data are available in the NRAO data archive basically within minutes as soon as the observation is done. We produce calibrated data, and I'll talk a little bit about that and the pipeline. So this uses the standard VLA calibration pipeline, but a specific VLASS recipe because we're observing VLASS, we can hard code certain things that we know we want the pipeline to do. The timescale for calibrated data takes days. So the pipeline running on one 4 to 8 hour VLA data set can take about 4 to 5 days. And then we have a quality assurance period. And that's just when one of the data analysts can get to it. And so that's during a working day, not on the weekends, not at night, but the time scale is roughly days. And then those calibrated data, or the calibrated data products that can be applied to the raw data to produce calibrated data, those are also served from the NRAO data archive as soon as they pass quality assurance. The main set of products that we've produced so far are known as quick look images. These are continuum Stokes images, so single plane images made from the 2 to 4 gigahertz data. This is also using the standard VLA imaging pipeline, again, using a particular VLASS recipe. The timescale that it takes is more like weeks. It first has to wait for the pipeline to pass quality assurance, the calibration pipeline, that is. And then the images can take another day or several days, depending on whether the imaging pipeline works right away. If the image that it's producing is pretty simple and straightforward, or if there's something very, very bright in the image or nearby in the image, then we might need to rerun the imaging pipeline with different parameters. Oh, I also want to mention, excuse me. Each of these images we produce is approximately 1 square degree. Each of the data sets that we observe is 80 square degrees to 160 square degrees. So we're producing 80 to 160 images from each VLASS, each individual VLASS observation. So these images don't go into the data archive immediately, but they are served at this link that I have here, science.nrao.edu/VLASS. They're available there immediately. And at some point at the end of an epoch, those images get uploaded into the data archive. There was an issue with epoch 1 with position offsets that I'll mention later. And the images in the data archive do not have those position corrected images, but the ones at this link that I put here do have the position corrected images. Okay, so that's what we've done mostly so far. What we are also producing are known as single epoch products. So these are, okay, so sorry, let me back up for a sec. The quick look images, and I'll talk about this more shortly, but they're using more simple imaging algorithms so that the images can be produced quickly and made available quickly so that they can be used to search for transients that someone might want to follow up right away. For single epoch products, we use a different pipeline recipe that I'll talk about that produces higher fidelity images, even for the same continuum image. And this takes much longer to produce. It can run for many days to actually many weeks to produce one of these images, depending on how complex the sky is. We will also be producing single epoch products that include spectral cubes and polarization cubes, so full Stokes, and catalogs that go along with each continuum image. So the original timescale was expected to be months to a year, but it turned out that the algorithms that were needed in CASA to produce the images weren't available, and a lot of development went into the pipeline recipe to determine how to produce good images. And so we fell very far behind. So we're now producing these single epoch continuum images as quickly as we can. And we're started with the first half of the second epoch, known as epoch 2.1. And we are serving those up at science.nrao.edu as well, and releasing them in chunks. And so we're starting with epoch 2.1 first, and only tiles with zenith distance less than 45 degrees, and I'll explain that a bit later. Okay, there also will be advanced data products, and so this is being done as a partnership with the astronomy community. So the main partnership is with CIRADA, which is the Canadian Initiative for Radio Astronomy Data Analysis. So they're using the images that we produce, and they've created a cutout service for not only VLASS images, but for other surveys as well. As you can see over on the right here, GLEAM, which is part, I believe that's from the MWA, the legacy VLA surveys, the infrared survey WISE, and then optical pan-stars and SDSS. So they're also producing a more sophisticated source catalog. So NRAO is not producing a source catalog at the moment for quick look data. CIRADA is doing that, and they're doing certain vetting of the catalogs. And then when they have when they have single epoch images available, single epoch cubes available with polarization information, they'll be producing Faraday rotation measures as well, and serving those to the community. Okay, so let me talk a little bit about the calibration pipeline. So actually all VLA data that's observed on the VLA is run through a standard calibration pipeline, and it runs on most data. It doesn't run on pulsar observations, and it requires certain standard setups. And I wasn't sure how much in depth to go into, so I basically here on this slide just given an overview of the different steps of the calibration pipeline. So there are a few a priori calibrations that can be done. So gain curves, so that's basically as the antennas move in different elevations, the antenna actually gets a little bit warped because of gravity. And as I said, it's, each one weighs over 200 tons. And so, so the gains actually change as a function of elevation, which is particularly important at the higher frequencies. We can also correct for known opacities because and the ionosphere as well, because we know where the antennas were pointing. So how much atmosphere they were pointing through, and we have ionospheric information as well. Switched power is what is used to correct for what I mentioned as gain compression before, but this should only be used in certain cases. Then data have the flux density scale set. All observations should observe a known flux density scale calibrator. Delay calibrations to correct for residual delays, basically from hardware, electronics. Basically, the data from the different antennas goes through slightly different lengths of cables. Bandpass calibration to correct for the spectral response, so the gains as a function of frequency. Then a complex gain calibration, or also known as phase calibration, to correct for the atmosphere, as the atmosphere was changing over time. That can change on the time scales of minutes. And then the flux density scale is set for the complex gain calibrator. And then polarization calibration, which was not available in the standard pipeline at the beginning of VLASS, but now because of the calibration used for VLASS has now been incorporated into the standard pipeline. So there's some basic polarization calibration as well. And so if you observe with the VLA, you will get data from the pipeline weblog. Obviously, this is very tiny. I'm not going to go through this whole thing. I just want to give a slight overview. There are various steps that do the various types of calibration that I mentioned on the previous slide. And there's a weblog where you can look through the different images that are, sorry, not different, plots that are made to show you the gain calibration solutions and so forth. And so you can get an idea if your data is good, if there's RFI, et cetera. And so if you want to learn more about this, I'm going to point you to a talk that was given as part of the 2022 data reduction workshop on the VLA pipeline. And you could just Google this, Google NRAO data reduction workshop, and you'd get to go through the whole pipeline and the different steps of standard calibration. So the VLASS calibration pipeline is basically the same underlying pipeline, but with some specifics for VLASS data. So we know that we're using a standard correlator setup and a standard integration time. And so we hard code some of the options, and we reduce some of the flagging that is done on standard data. So for example, we set a short solution interval for the gain calibrations to 0.45 seconds because we know that that's the integration time. We use the switch power to correct for the gain compression. And we also turn off flagging statistics, which saves a lot of time. So the calibration pipeline runs much faster. So over the past several years, there have been improvements to the standard VLA pipeline that came from VLA Sky Survey development. So for example, that applying the switch power and that compression fix to correct for gain compression, that came from development for the VLA Sky Survey. This should only be applied to 8-bit data, not to 3-bit data. For calibrators that are not point sources, and I'll talk about this in the next couple of slides, I think, as well. UV ranges for calibrators that are not point sources. The standard calibration assumes that phase calibrators are point sources, so that all the phases for should be 0. So any phase that's not 0 is due to the atmosphere or to the electronics. But if your source is not a point source, then that messes up that calibration. There's also improved flagging heuristics for RFI. And as I mentioned, polarization calibration was originally put into the pipeline for VLASS and then incorporated into the standard pipeline as well. Okay, so I mentioned gain compression a few times. It really is quite a big issue, especially at S-band because of the satellite downlinks and the Sirius XM satellite radio. So the amount of gain compression is determined by switch power signals. This is internal to the VLA system. Switch power is there's a switch with basically I think it's like half a hertz that turns on and turns off, like it adds extra signal to the system. And so you can determine from the known addition, the addition of a known signal and compare the output to see whether the output is in a linear part of the scale or whether it's gain compressed. So this is corrected by basically fitting a template to the compression versus time for each individual antenna and basically dividing that out. So what happens is with gain compression, the gains are still linear, but with a different linear slope than the standard. And this can be this can be fixed when the compression is not worse than approximately 30%. And so you'll see these are these are figures that you'll see in your calibration pipeline weblog. So on the left is when we expect to see the gain response close to 1. For a badly compressed data set, the gain responses would be much less than 1. And then if we see the compression versus time dropping down below 0.7, then that's something that can't really be corrected. Okay, I mentioned UV ranges for resolved calibrators. So the standard gain calibration assumes that the phase calibrator is a point source. And so what we define as a point source is, so shown here in this plot on the right is the residual amplitudes as a function of the UV distance, here shown in kilolambda, so a number of wavelengths. And we estimate that something that is within 3% of a point source, the residual amplitudes are less than 3%. That's good enough for the pipeline. However, sometimes the phase calibrators just aren't actually a very good point source, and some of the information in the VLA calibrator database is a bit out of date. And so what we do is we can select a UV range where the residual amplitudes are less than 3%, and that basically tells the pipeline ignore baselines where the calibrator does not look like a point source, where it looks resolved, and only use baselines where it is a point source in order to get the antenna gains. And that's easy to do, of course, because we have 27 antennas, and so there's 27 times 26 baselines. So it's okay to drop some out and still be able to calculate the gains for an antenna. Okay, so here's an example of one that that does not look like a point source at all. There's basically there's no UV range. There's no significant UV range you can find where this source, where the residual amplitudes are less than 3%. So one thing that a user could do in this case is basically make a model of their gain calibrator and then tell the calibration pipeline, this is not a point source. This is what the source actually looks like. I've given you a model for what the source looks like, and that allows you to get the gains more correctly. So there was some development basically that did a comparison of VLA sky survey images made with data that were calibrated with a point source, with a source like this that was not a point source, where either a model was used or a point source was still assumed. And it turned out that for the VLA sky survey, the improvement of the images was not enough to make it worthwhile to put in models for the gain calibrators. And there was a memo published by John Tobin and myself in the VLASS memo series, memo number 19, that basically shows the results of this and the comparison of images made with and without using a model for the phase calibrator. So the VLA Sky Survey specifically chooses certain phase calibrators and attempts to use ones that are most like a point source. And so it didn't always do well, but what I want to give is a caveat that it's unclear that this conclusion of not needing to use models, it's not clear how well that applies to non-VLASS data. So we would probably still recommend to users that if they have a phase calibrator that's not a point source, that they might want to make a model of it. Okay, so I'm going to now start talking about creating images. So first, give a little overview of the imaging workflow. So the calibration goes through quality assurance and passes quality assurance, and then that calibrated data set, which covers 80 to 160 degrees squared of the sky, gets chopped up into individual little data sets, each of which can be used to make a single 1 square degree image. And those data run through the imaging pipeline. Basically, we have many different computing cores, so they can all run one imaging pipeline on their own. So images are made, and about 80% of them are actually acceptable on the first round through. They pass our statistics, they look good, and about 20% of them, something needs to be done differently in the imaging pipeline. And that again is because of the nature of the sky. If there's a very bright source in the image or just outside the image, it makes it harder to deconvolve the image, and so we'll then reprocess the images with different input imaging parameters. This is all done in NRAO's CASA software using the T-Clean to do the deconvolution. And so we basically run with different T-Clean input parameters to try to create an image that can be deconvolved even in the face of a very bright source. So first, the quick look pipeline. So as I mentioned, this is really very basic imaging, and the point is to get something very fast, even if it's not the best scientific quality. It's good enough to identify where there are sources and roughly what their flux density is, so that there can be comparisons with previous epochs of the VLA sky survey or with other survey data, basically to identify transients. So the quick looks, the quick look images are Stokes eye continuum, a single plane made of combining the 2 to 4 gigahertz. We use the T-Clean mosaic gritter. That's important, and I'll mention that a bit later. And here's the very simple stages of the imaging pipeline. So this is what part of the weblog looks like. So first, the parameters for the input for the image are defined, basically the parameters to use for T-Clean to create the image. An initial image is created, and then it's corrected for the primary beam. We make an RMS image basically from the residual image. We smooth the residual image combined with the final image to get the noise as a function of location in the sky. And then we extract the final sub image. So what we actually do is make an image that is 2 by 2 degrees, so 4 square degrees. And then we subtract out the central, not subtract out, we select out the central 1 square degree. So this is important in order to avoid aliasing into the edges of the image. So we actually have to make a much larger image and then select out just the 1 square degree that we want. So issues with quick look, the images still contain some deconvolution errors. You know, you see side lobes from bright sources. The pixel sizes we use 1 arcsecond pixels. This is not very good sampling of the synthesized beam, which is about 2.5 arcseconds. To get good sampling of the synthesized beam, what you really want is 4 to 6 pixels across the minor axis of the beam. So this makes it harder to deconvolve, and that leads to errors in deconvolution as well. There can be phase errors from the complex gain calibrator. We don't use any clean mass or clean regions, and we don't correct for the W term, which I'll mention. I'll talk about later. Oh, I'll talk about it right now. Okay, so when you're imaging the radio sky, you're basically making an implicit assumption that the sky is flat, and that you're getting flat plane waves coming in. But depending on how large the image is as a function of frequency, that fails to be a good approximation. And this leads to deconvolution errors as well. And so it actually gives position offsets. So it puts the emission in the wrong location if you don't correct for this this W term. So what we did was first produce the images and then do comparisons to between VLASS positions and Gaia, and VLASS positions and positions from long baseline interferometry, to basically see what the offsets were, and then we can do an analytical correction for each image. Now, T-Clean has a different gritter than the mosaic gritter, the AW project gritter, and this corrects for the W terms, and so we wouldn't need to do after the fact corrections, which are per image, not per source. So the AW project gritter actually does a much better job of this, but it is much slower, and so it's actually, in order to apply this to the entire VLA sky survey, would take years, it turns out, with the CPUs, with the computers that we're using. So we use the mosaic gritter when possible. So we're using the mosaic gritter for quick look images, and we're putting in a position correction for each image. Oh, I am running out of time. Okay. So I'll try to speed up a bit. So I wanted to talk a little bit about the quality assurance. So we use statistics to basically determine whether the image was able to be cleaned correctly, but there are still sometimes artifacts that needed to be identified visually. So here's just some of the statistics that we use to determine if an image is good. And then if the statistics were not good, we could reprocess the image with different T-clean input parameters. Oh, here's what the pipeline weblog looks like. So I'm showing here on the top left image is the image itself. It's quite zoomed out, so you really can't see very much. But then the next image to the right is the RMS image, so you can see how the noise, what the noise properties are. There's also an image of the point spread function. Again, you have to zoom in to see something good here. The point is that artifacts show up in this here if there were some. This is actually a good image. I'll show an example of artifacts. I will skip this because I already mentioned that. So here's an example of different artifacts that we commonly see. So what we refer to as bad baselines, these are individual baselines that might have high weights and lead to fringes across the image that are clearly non-physical, and they show up quite easily in the RMS image. RFI, if there is a brief moment of radio frequency interference, it shows up in a VLASS image at a specific location. Because we're constantly scanning the sky, each field that we're observing was observed at a different time, and so RFI at a specific time shows up in a specific location, and that's easy to identify as well from the RMS images. And then I won't go into the other two. We can ask me about them if you're interested. But the point is that we basically the statistics of an image did not tell us whether these artifacts were there. So originally, every image had to be looked at individually. The data analysts themselves actually came up with procedures to heuristics, as well as experimenting with convolutional neural networks to identify these artifacts automatically so that images don't need to be looked at visually. And this actually greatly speeds up the quality assurance process. Here's the very first quick look image that was made that it actually had a lot of interesting sources in it. And so this is just to show the 1 square degree image compared to the instantaneous field of view of the sky survey and the synthesized beam, or the angular resolution element. Okay, so I do want to talk about single epoch continuum images and how they're made differently from quick look images. So these use smaller pixels, which better sample the synthesized beam. They use clean masks made from internal catalogs from quick look sources, and they iterate in different stages of imaging. The most important thing is that we use self-calibration to improve the data model to get a better image. So this is the procedure to create single epoch continuum images. We get an initial model from an initial image. We create a mask from that image. We use self-calibration. We smooth this, and then we image again, smooth the second image to get an improved mask, and then do a few final stages of imaging with the different masks in order to produce a final image. And similar to quick look, there are some times when this just doesn't work that well the first time around, and then we would rerun the pipeline with different input parameters to try to do a better job. So here's a comparison of a quick look image and the single epoch continuum image, and we can see we get much better RMS. So this is a pretty tough example because there's an extended source, and the high resolution of the VLA sky survey doesn't always do well with extended sources, but the single epoch pipeline cleaned this one up nicely. Here's another example that's nicely cleaned up, and this is from the self-calibration that cleans this up so nicely. Okay, but even with single epoch continuum images, we're attempting to use the mosaic gritter, but this only works well for zenith distances less than 45 degrees. So what is actually happening here is that as we're looking through more atmosphere further away from the zenith, the different frequencies, red and blue, actually shift by different amounts. So the red end of the S-band, the 2 gigahertz end, has a larger offset from its true position than the blue end. So the overall displacements are pretty small for zenith distances less than 45 degrees. And so for those areas of sky, we continue to use the mosaic gritter. The AW project gritter corrects for these, and so we will be using the AW project gritter to make single epoch images for zenith distances greater than 45 degrees. The main problem this causes for us actually isn't the positions, which, as I noted, we can correct for with a mean position correction per image, but it actually really messes up the spectral index if we don't account for this issue. So we have some pretty significant computing challenges. We produce 35,500 1 square degree images per epoch, and that's times three epochs. A quick look image, an easy quick look image takes a half a day to run through the pipeline. An easy single epoch continuum image can take a few days. We'll need AW projection for images and tiles in the south. So there's development going on to create a new GPU-based gritter that will allow much faster processing of AW, running T-Clean with the AW project gritter. And it's about a 14 times improvement in processing speed. So development is still ongoing for that. We haven't started using it in production yet. Future development that's being worked on for VLASS. Peeling to improve imaging for direction-dependent effects. So there's work going on right now. Oh, I wrote for mosaic gritter. I meant for mosaics, not for the mosaic gritter, but for mosaic images. And so that's work right now being done by staff member Viral Parekh. We need to figure out quality assurance procedures for the polarization products, which we have not actually started producing yet because we're working on the single epoch continuum images. We will further automate quality assurance procedures and we'll validate the GPU gritter. I'm going to skip the science highlights in the interest of time and just tell you the status. We are currently observing the last half of the third epoch, and quick look is in progress. And when we're not doing quick look, we're working on single epoch continuum images. And right now we've started with 2.1, that's basically where we were when we started producing single epoch continuum images, and it's been a slow process. There's actually the possibility of a fourth epoch. This is the slide I meant to show. So showing different radio surveys and instruments and their availability as a function of time. So DSA 2000 is going to come online later this decade, and then NGVLA later in the next decade. And so the VLA Sky Survey and Epoch 4 would nicely bridge the gap between Epoch 3 and what will be available in the future. This will also allow us to produce deeper cumulative images and get to the point where star-forming galaxies start dominating over AGN. So even though we're not going that much fainter, most of the new sources, or about half of the new sources, would actually be star-forming galaxies. And we expect about 1,000 new transients per epoch as well. So there was a review put forth by the community that we work with closely, and there will be a review in September of this year to determine whether or not we will do a fourth epoch, because you get a lot of good things out of it, but a lot of staff time goes into producing it. And I will just end on this slide that shows resources. Clearly, there's a lot more than I could possibly talk about in this talk, but at the Survey Science website, there are guides for how to use and how to access different product types. Many quick look images are also available in the archive as well, and we're starting to produce single epoch images. We've got about 3,500 of them now, and I'll point everyone to Serata for image cutouts, and then to the survey paper by Mark Lacey. There's a VLASS memo series, and for any questions about how to access or how to use the data, you can email the VLA, the NRAO help desk, which has a VLASS department. And I will end there and hopefully take questions.
Thank you. Please unmute yourself and ask the question. I had one question about the RFI compression, the gain compression that you showed.
Mm-hmm.
Are these RFI sort of persistent RFI, or they come and go, or is there some like, do you have some times when these are uh, like uh, like how do they occur?
So it's pretty persistent in certain parts of the sky near the Clark belt. And then there are other times when someone just might be following a source that's somewhere else in the sky that just happens to, a satellite happens to go across. So it's unfortunately not very predictable. So for in general, for the VLA sky survey, it is pretty predictable because it's mostly coming from those satellites in the Clark belt at S-band. But it's a big problem for everyone's data as well. And if you're a VLA user, I recommend using the 8-bit system when you set up your correlator tuning, because it's easier to correct, or you can correct for compression with the 8-bit system. Is there anything anyone wishes that I had covered that I didn't manage to talk about?
Please unmute and ask question if you have. I think to learn about the possible fourth epoch is really nice. So definitely, we are already using VLAs as images. We have used it for our science. And if we get the fourth epoch, I think everything will improve and it'll be really nice.
I think it's likely to happen, but I think that it will further delay the production of the single epoch products, particularly polarization. It's just turned out to be much more complicated in terms of just computing and job management. So, not even the necessarily the development of images or the observing, but just having enough computing processes and making sure that the computer cores stay healthy and aren't crashing. We've had a big problem with that, and it's really slowed things down in a way that was really unexpected, unfortunately.
There's one question in the chat box.
The uniformity of the sensitivity across the sky. So unfortunately, I can only sort of give you qualitatively. I'd have to remind myself by calculating this. But basically, when you're doing any kind of mosaic, the more, the closer spaced your fields are, the more homogeneous your noise will be, your sensitivity will be. And that's because the sensitivity pattern is basically a two-dimensional Gaussian across the sky, right? Your primary beam is most sensitive at where you're exactly pointing, and then drops off with a Gaussian shape. And so you want is enough overlap in those two-dimensional Gaussians. Okay, so how much flux gets affected is your question. I think I would have to look it up, but I think we're aiming for something like 3 to 5% homogeneity across the sky. So we're quite homogeneous when we're scanning across in a single row, because there's very little separation. There's only 1.4 arc minutes of separation. But then between the rows, it's 7.2 arc minutes. So maybe it's worse than 3 to 5%, because what the primary beam of S-band at 3 gigahertz is 14 arc minutes. So the separation between two rows is half a primary beam at the center of S-band. So we'll have more homogeneity at 2 gigahertz, where the primary beam is larger, and then will be less homogeneous at the high frequencies at 4 gigahertz, where the primary beam is smaller. But of course, most sources in the radio are either have a flat spectral index or they're brighter at the lower frequency. And so most of your emission from your sources is coming where you have more homogeneity, more uniformity across the sky.
Yeah, anyone else would like to ask a question? Let's go ahead. So how much of the pipeline was ready at the beginning of the survey, and did it evolve over the years? And so how was the pipeline aspect of the data analysis handled as the survey progressed?
So first, there was just the main issue with getting the okay, yes, most of the pipeline was available as a standard pipeline with the standard calibration procedures. What was really problematic for the VLA Sky Survey was the huge amount of metadata. So we're doing, a 4-hour observation, or and I see another question I'll get to in a second in the chat. A 4-hour observation, 6-hour or 8-hour observation with 0.45 second integration times. And all those fields with OTF have different positions. So actually what was the data rate is not very huge, but the metadata rate is really huge. So it turned out that various things like set Jansky, setting, there's a huge number of visibilities in the data set because basically that have to be kept track of. So it would take at first it would take something like 3 days just to run set JY on the data. And I don't remember what particularly got fixed there. So the compression fix was added later. That was added, I think, maybe in epoch 1.2, the second half of the first epoch. The imaging pipeline did not actually exist yet for VLA. That was a modified version of the ALMA imaging pipeline originally. Yeah. So there continues to be development. RFI heuristics in particular is something that's still being worked on.
Yeah. Thank you.
So there's a question in the chat, is there any particular reason of choosing S-band? The answer is yes. So there's a couple different reasons. So the legacy surveys were done in L-band, so 1.4 gigahertz. So using S-band partly gives us a lever arm for calculating spectral indices for sources that are non-variable to compare between VLASS and earlier surveys. The fractional bandwidth is quite large, so it's from 2 to 4 gigahertz. So this allows us to get spectral indices in band. So that was also important as well. And then finally, for to get Faraday rotation measures, you actually want something at lower frequencies as well. I think it's because the Faraday rotation goes as lambda squared. So the lowest frequency spectral window is actually quite important for getting good rotation measures. So all of those sort of pointed to S-band. There's also the reason of if you're at higher frequencies, you have a smaller primary beam, and so it would just take a lot longer to do the same survey. There were certainly suggestions for surveys at other frequencies, but S-band seemed to be a good sort of compromise between all the things that were wanted and all the things that you could get out of it. So I think what's particularly powerful about the VLA Sky Survey is that you basically now have high resolution information about any source in the VLA sky, to the depth. But that's new. The first survey was the previous one with the VLA that was somewhat high resolution, but VLASS is twice as high resolution. and covers a much larger area of sky than FIRST. FIRST was designed to cover the same region of sky as the Sloan Digital Sky Survey. And so VLASS gets high resolution and covers the entire sky, and using S-band made that sort of possible with the amount of time that we wanted to be available for our sky survey. One more question. How are you going to get spectral index in the observing frequency band? With what accuracy? Yeah, it's not very accurate for faint sources. For brighter sources, let's see, above maybe a few hundred, maybe about above a millijansky, you can do pretty good with about 0.05 to 0.1. So we're getting spectral index that actually comes out of T-clean. We use multi-frequency synthesis to get spectral indices, and so it's just a standard part of the T-clean and deconvolution algorithm. But we will also be producing spectral cubes as well, so we'll be able to get better spectral index information for even for faint sources. So we have 16 spectral windows across the 2 to 4 gigahertz frequency band, so each one 128 megahertz wide. And so we'll be producing what we call coarse cubes, and those are cubes in both polarization and in frequency. So we'll be producing IQU for every spectral window, and possibly V. That's still under discussion.
I wanted to ask one thing about the resolved calibrators that you mentioned. So, so for the resolved ones, you said that, so are these models available somewhere? Like,
unfortunately, no, the models are not available. So actually, I should have mentioned, this is not for VLA Sky Survey, since, as I said, the memo concluded that we don't need those models, but there's still a clamor from the community and from actually the data analysts and scientists in particular here to be able to run the pipeline with models for phase calibrators. The way that would probably be done is the models would be done on the fly. So you would make an image of the phase calibrator and use that as your model. And instead of creating models for everything and having them available.
okay, so for VLASS, sorry, so for VLASS, you had to move on with basically where the calibrators turned out to be resolved. You moved on with self-calibration and did not use the phase calibrator itself.
Yes, so that's basically, we use the phase calibrator for the initial calibration, and then for single epoch continuum imaging we do self-calibration. And yeah, that's actually I think the main reason why we don't need better models for the phase calibrators themselves, because we can do self-calibration using bright sources in the field.
Yeah, that's sometimes the case at low frequencies, but meaning I didn't know that at these frequencies also you could proceed with self-calibration case of a failure of phase cal. Okay. Any question? We can maybe take another minute if there is any pressing question. Okay, I think it's a good time to conclude. Thank you very much, Amy, for your time and this great talk. And we are very glad to learn about the latest from the VLASS, and we look forward to using this survey in our work. So thank you very much for your time. Thank you very much for all of you to attend, and see you all at the next RATeS seminar. So
thanks everybody for calling in so late.
Thank you. Yeah, bye.